Medullary countercurrent system requires us to focus on the loop of Henle. So remember, the loop of Henle has a descending limb and an ascending limb, and the walls of these parts of the loop are going to be a little bit different. So remember that during its movement through the proximal tubule, filtrate is going to be passing through this tubule and sodium is being reabsorbed. And so we have a constant rate of sodium reabsorption. That's a sodium. There we go. And then when it comes down the descending limb, we're going to be impermeable to sodium. And then on the ascending limb, we're going to use active transport to remove sodium. And then in our distal tubule, we're going to, and the collecting tubule, we're going to see variable sodium reabsorption. So what that means is it's going to be reabsorbed only if we need it. So sometimes it's called variable sodium reabsorption, sometimes it's called hormonally controlled. And you'll likely see a question asking, where in the nephron would you have constant sodium reabsorption, and where would you see it hormonally controlled? Well, this part of the distal and the collecting tubule, we see it under the influence of hormones, whereas it's going to be constant here. It's constant here because it doesn't change. It's never going to pass the descending limb of the loop of Henle. Okay, so that is constant because it doesn't change, even though we're not reabsorbing any sodium here. And then on the ascending limb, we're always reabsorbing sodium. And so proximal, descending, and ascending are all going to have a constant rate of sodium reabsorption, whereas our distal and collecting tubule are going to have this variable rate of sodium reabsorption that's hormonally controlled. So now that we understand where sodium is reabsorbed, we want to think about where water is going to be reabsorbed. So remember that we're not reabsorbing sodium on our descending limb, and that's because we are going to be reabsorbing water. So I'll say permeable to water. Okay. And then, I'm missing an M there. On the ascending limb, we see the reverse. So basically, we're going to reverse our permeability. So we'll be impermeable to water on our ascending limb. But remember, we're using our active transport. So we're using energy to reabsorb our sodium. Right. So sodium's coming out here. And our water, I'm using purple for water today. Water's coming out on the descending limb. Now, if we let the water stay and we let the sodium stay, this outside of the tubule, the interstitial fluid, would kind of cancel each other out. The water would dilute all that sodium. So we're going to get rid of the water by putting it in our paratubular capillaries and taking it away from the loop of Henle. So we take the water away, but we leave the sodium. And that's what establishes our vertical osmotic gradient. And so as we go down towards the medulla of our kidney, and we go further from that nephron, we're going to see our osmolarity increase. And so the amount of sodium increases as we get further away from our proximal and distal tubules. Okay, so it's going to get more and more salty down here towards the bottom of the loop of Henle. And that's a good thing, because as long as it's really salty out here, we're able to pull more of our water out of that descending limb. Because remember, the descending limb is impermeable to sodium, but it's going to be permeable to water. And so that sets up a lot of osmotic pressure out here. And so the water is going to move towards that greater osmolarity. It's going to go towards all that salt. Once it's out of our tubule, then remember, it gets put in the circulatory system and taken away. So we've got our vertical osmotic gradient for sodium, getting more and more salty as we go towards the medulla and towards the bottom of the loop of Henle. And then we're going to be taking our water out of that descending limb and taking it away through the peritubular capillaries. Now, once we get up to the distal tubule and the collecting tubule, remember that these are going to be hormonally controlled. And so if we have plenty of water, we're not going to reabsorb any more. So whatever's left in the filtrate at the top of our ascending limb, whatever water is left, it's going to be excreted. But if we need more water and we want to get back some water that is still in the filtrate, we're going to use vasopressin, also known as antidiuretic hormone. And vasopressin is going to go to our collecting tubule and our distal tubule, and it's going to trigger those tubular cells. So I'm drawing a tubular cell. And then on the right would be my basolateral membrane. And then on the left would be the luminal membrane facing the filtrate. And so when the vasopressin goes to these tubular cells, it's going to use the second messenger pathway to trigger the insertion of more aquaporins on that luminal membrane. Okay, so these aquaporins are going to allow water to diffuse into the cell. And then once it's inside the cell, it can diffuse out across that basolateral membrane. And so that's going to allow water to get pulled out of our tubule, okay, our collecting tubule, and we do it also on our distal tubule. So we're pulling more water out. Now remember our vertical osmotic gradient. The further we go down, the more salty it becomes out here. And so the more salty it is out here, the more water is going to come out. So as filtrate moves down that collecting tubule, it's going to be subject to the saltiness outside, and that's going to pull more water out. And so that way, by the time this filtrate is excreted, we're going to create a really concentrated filtrate, or really concentrated urine. And that's going to help us save water. But if we had plenty, we would not have vasopressin, and we would not use this pathway, the second messenger pathway, to put aquaporins, the little square there, the aquaporins, on the luminal surface of our tubular cells. And we would not reabsorb water. And so if we didn't need to reabsorb water, we would leave it all in the tubule, and that would produce a more diluted urine. And so we would lose more water than we would if we were using our vasopressin to grab it back.